Hello, everyone. Today we are going to be presenting our project using iron oxide nanocrystals to mimic the tactile senses of skin. I'm George.
I'm Vishal.
I'm Yo-Yo.
I'm Samantha.
I'm Holden.
So, why does synthetic skin matter? Why is it important to us? Well, basically, if we are able to create a synthetic skin that can sense and detect pressure, we can help return the sense of touch to amputees, including those who have fought hard for our country. It is necessary that we work hard to help these amputees respond to certain stimuli that are very important for survival, including pressure, so that they may feel once again.
But before we can create a synthetic skin, we have to understand how human skin works. Now, there are four types of mechanoreceptors in human skin: Merkel's discs, Mesner's corpuscles, Pacinian corpuscles, and Ruffini endings, as you can see here. These sense soft touch, vibration, stretching, and high pressure, respectively. We understand that it would be impossible to mimic all of these senses in just 1 week, so we decided to focus mainly on the Ruffini endings, which detect pressure. When pressure is exerted on the skin, the Ruffini endings compress, which makes sense given their pump-like shape. And when the Ruffini ending is compressed, an electric signal is emitted through the nerves.
We believed that our synthetic skin would be receptive to pressure because when our skin is pushed closer together, the nanoparticles are able to pass current with more ease, and therefore the skin becomes more conductive.
Now, now that we understand how human skin works, we can discuss the synthetic skin. Now remember, the goal for our synthetic skin is to detect pressure. So on the left, we have an image of the actual synthetic skin that we created. And on the right, there's a cartoon diagram that will help us explain our synthetic skin in more detail.
So our synthetic skin has two parts. The first part is the PDMS, which you can see as the blue block on the screen. The PDMS is a synthetic rubber, so it is both flexible and insulating, just like human skin is. The second component is the iron oxide nanocrystals, which you can see as the black dots in the diagram. The nanocrystals are embedded into the PDMS, and together the PDMS and the nanocrystals can allow us to detect pressure with our synthetic skin.
So to make our synthetic skin, we needed something that's rubbery and stretchy like our own skin. So we decided to use a silicone rubber gel called PDMS. So when we made our PDMS, we used a base and a curing agent that react when it gets heated up. And since PDMS is really insulating, we added iron oxide nanocrystals in order to conduct electricity better.
So we've talked a lot about synthetic skin and what it's made of. Now I'm going to explain how it actually works. On the right, you can see a zoomed-in image of the synthetic skin. The black dots are the iron oxide nanocrystals, which are electrically conductive. The white background is the PDMS, which is an insulator. Current flows between the red and black terminals of the multimeter when electrons jump from black dot to black dot, or from nanocrystal to nanocrystal. Conductivity increases with pressure, which is depicted in the two diagrams. The left-hand diagram is a zoomed-in image of our synthetic skin when no additional pressure is applied. As you can see, the black dots, or the nanocrystals, are quite far apart. This makes it difficult for the electrons to jump from black dot to black dot, or from nanocrystal to nanocrystal. Because it's so difficult, there's only one or very few paths that the electrons can take between the terminals of the multimeter. So when there is no additional pressure applied to our synthetic skin, it has very high resistance and low conductivity. This is sharply contrasted in the diagram to the right, which is a zoomed-in image of our synthetic skin when there's high pressure applied. When pressure is applied on the surface of skin, the skin is actually squeezed together. So the black iron oxide nanocrystals are actually closer together. This short distance allows electrons to very easily jump between nanocrystals. So it's very easy for them to get from one terminal to the other. It's also because it's so easy for them to jump from dot to dot, the electrons can travel on multiple different paths. So when there's high pressure applied to our synthetic skin, it has a very low resistance and high conductivity.
So we wanted to test out just how well our skin could detect pressure. To do this, we measured the resistance of the synthetic skin when we squeezed it and when we released it. As you can see in the video on the right, when pressure is applied, the resistance drastically drops compared to when no pressure is applied.
This is the graph we produced from our data. Note that lower resistance corresponds to high electrical conductivity, as the electrons can move far more easily. So the four plateaus that are circled in red on the graph are the resistances when no pressure was applied. These are the highest points on the graph, because when no pressure was applied, the nanocrystals were quite far apart, as I spoke about earlier. As you can see, the resistance always returned to nearly the same value, because at each of these four intervals circled in red, no additional pressure was applied. So the green, purple, and orange highlighted sections on the graph are when pressure was actually applied. The most pressure was applied in the orange section, while the least was applied in the green section. As more and more pressure is applied, the resistance continuously decreases. Thus, the synthetic skin can differentiate between different amounts of pressure. This result is quite remarkable, as it means that our synthetic skin can not only detect pressure, but it can differentiate between varying amounts of pressure, just like human skin does.
We also tested the conductivity of our synthetic skin quantitatively by pressing a known weight onto it. In this case, we added 50 milliliters of a heavy sugar solution every minute and recorded its resistance every 2 seconds. When graphing our data points, we found that there is an exponential relationship between the resistance and the weight of the solution. We can conclude two things from this. One, our calibration curve allows us to calculate the weight of a surface based on the resistance that it experiences. And two, similar to our own skin, the synthetic skin is more responsive to small pressures than large ones. For example, you could easily feel the difference between a fly and like a raspberry, but the difference between a watermelon and a poodle would be much harder to compare.
So, after conducting our experiments, we were able to conclude that the mixture of iron oxide nanocrystals and PDMS can conduct electricity, and the synthetic skin model that we made can sense pressure through the changes in resistance across the suspension. In the future, we hope that the synthetic skin may be connected to the user's nerves so that the user may instantly recognize when different amounts of pressure have been exerted on their skin. Also, in the future, synthetic skin may be designed to respond to different types of stimuli, including changes in temperature and vibrations, and these would allow the user with synthetic skin to feel almost exactly how they will with real skin. And this man on the right, as well as many others, would be able to benefit tremendously from this technology. Thank you.
So the question was, did we do some preliminary research on what has already been done with synthetic skin? So we did some research on the current applications, especially in the medical field, and we found that skin grafts are used far more commonly than synthetic skin. We also looked at some research that one of our instructors, Stephen, did to see some of his results, and he found that, while he did no experiment, he found that this field would be quite promising. So based on that, we decided to do an experiment and see if we could make synthetic skin of our own.
It's very striking how much the resistance in the synthetic skin changed with pressure. Did you make any effort to try to measure how much the width of the skin compressed when you would have it at these different weights or different squeezings by hand?
So the question was, did we make any effort to measure how the squeezing affected the width, correct? Well, we did not measure this quantitatively, but when we were doing the actual squeezing, we found that because the skin was quite thin, I mean, it is supposed to be like skin, there was not a measurable difference. So while it might have compressed a few millimeters, it wasn't like it went from very thick to extremely thin. It is a rubber, so it doesn't compress that much.
Did you guys make any attempt to actually measure the amount of pressure that you were applying for your systems? Because you talked about a little, like small pressure, medium pressure, I think, and large pressure. Do you know what those values are?
Why don't you talk about that?
Sure. Well, for the qualitative experiment that we did use our fingers, so it's not exact how much pressure was put on. But we also conducted an experiment that's quantitative, where we measure the amount of weight that's being pressed onto the synthetic skin, so that we can create a graph.
So this graph was used to make a calibration curve. So at a given resistance, we can show how much weight is being applied to any surface. And knowing the weight on the surface, we could calculate the pressure and the force being applied to the surface if we knew more about the weight distribution and the dimensions of our skin.
Could you go back to the previous slide? Because you have your resistance in microoms here, or on the sugar solution slide.
Yeah.
And those should be comparable to the resistance that you're measuring with the pressing, right?
Yes. Let me. So on the multimeter.
Yeah, the one before this.
Sorry. Here.
Yeah, because they kind of line up. I think when, so this is an Oxide, it's got like 170 megahms.
Okay. And then here.
So you created a calibration curve.
Mhm.
And so then you can take that calibration curve and calculate out the amount of pressure you put on in terms of weight based on the calibration curve that you created.
So can you repeat the question?
So basically, 17 it's a fairly small amount of mass.
So as you pointed out, they are different, but I believe this was a different sample from a new batch of skin that we made, because we made the skins in the two batches for two different experiments. So because we could not control exactly how many nanocrystals were in it and in what proportions, it makes sense that the results are not don't match up completely.
I was just saying that you could have used this graph to calculate the pressure when you're squeezing it, because this is a calibration curve.
Right.
This is relative only to one sample, and then the other graph, the squeezing, was relative only to that sample.
Any other questions? Okay. Thank you.